Today we're going to talk about Hess's Law. We're going to start by looking at the term enthalpy. So the change in enthalpy is independent of the pathway of the process. So what does that mean? When we're figuring out the heat of a reaction, many reactions go through many steps. And so as they go through those steps, it doesn't matter how many steps it takes to get from the beginning to the end. It just matters that we get there. And so you'll see this as we get into the problems of this reaction. We refer to enthalpy as something called a state function because it doesn't matter how we get there. So in going from a set of reactions to a set of products, delta H is the same whether the reaction takes place in one step or a series of steps. A good analogy of this is if you're going from chemistry class down to the cafeteria, you can go out the hall, down the steps, the stairwell in the corner, go down to the first floor and go straight to the cafeteria. You could also go down to the second floor, go to the gym, to the locker room to pick up something you forgot, stop by a resource center, go back up to the third floor to turn a paper in, and then go back down to the first floor and to the cafeteria. It doesn't matter. You ended up in the same place. You left the same place and you ended up in the same place. It doesn't matter that one route was more direct and one route was more took more time. So there's two rules to follow when we are doing this. One is that if a reaction is reversed, the sign of delta H, the enthalpy, is also reversed. And two is the magnitude of delta H is directly proportional to the quantities of the reactants and products in a reaction. So if we change a reaction from one direction to the other, we're going to change the positive and the negative. If we multiply a reaction through by 2, and let's say the enthalpy was 25, we're going to double that enthalpy up to 50. So how do we go about solving problems? Well, we need partial step equations to add up to our overall equation. And this is a great video to watch more than once because this background information doesn't make as much sense until we get to the problems. But we can't do the problems until we have covered the background information. So this would be one that would be worth, hitting play and watching again. So we can manipulate our equations in two ways. One, we can reverse the entire equation, so we can switch it the other way around. Or we can multiply the entire equation by a factor, usually doubling, but it could be tripling, it could be quadrupling. Or we can do both. We could do both to an equation. So keep in mind that whatever you do to the equation, you must do to the enthalpy value. This will make a whole lot more sense once we get into some of these problems. Okay, so here's our first problem. Essentially what's given to you here is the answer. And we're looking to find the delta H for this reaction. We're trying to figure out what it is. These G's just stand for gas. The font made it capital, so that's why those are there. The information we need to solve this problem are these two partial step equations. These are the equations that are going to get us from the partial steps up to this final answer. Okay, so we need to add these equations up to equal this overall answer. We notice that we have an enthalpy here. This one is positive, this one is negative. The positive one tells us that it's endothermic, and so this is a reactant. And so I sometimes think it's easier to just go ahead and put this right into the reaction. Then I don't have to worry about reversing signs or remember to reverse signs. This one is negative, which tells us that it's a product in the reaction. Even though it's negative, once it's part of the reaction, it just stays as positive. So what we're looking to do is to add these equations together to equal this equation. Okay, so what I'm going to look at is I'm going to look for things that are unique to my final equation, my answer, and unique to these equations. So meaning that N2 is here, and the only place down here that I see N2 is right there. I see O2 in both of my reactions. I see NO, which isn't a part of my reaction at all. And so that's what's referred to as an intermediate. It's something that is produced and then used up in the steps of the reaction. I also see NO2, which is unique to all of these parts and unique to my reaction up here. So those are the ones that I'm going to base my decision making on. Since N2 is a reactant here and N2 is a reactant here, I'm just going to go ahead and copy my reaction exactly how it is. And then I'm going to look here and I said, well, this is a product and this is a product. Notice I haven't thought too much about the thing, but these are products and they're on the proper side, so I'm just going to go ahead and also recopy this reaction, keeping in mind that my arrows must line up, or this becomes very difficult to do. So I'm just recopying. Okay. Now, I'm going to go ahead and add these equations together. So I'm going to add them going down, but if I have things on opposite sides, I can cancel out. This is like in algebra when you're adding two linear equations. It's the same sort of idea. So I have NO on this side, and I have NO on this side of this equation, and so this and this can cancel out. The rest of this I can just sort of bring down, and we'll worry about the kilojoules at the end, but N2 isn't going to add with anything, so it's just N2 gas. O2, well, I have one O2 and I have two O2, so now I have two O2 gas. And here I have two NO2 gas. So that matches now my answer, the equation that I was trying to get. The last thing I have to figure out is how many kilojoules. Well, I have 112 kilojoules on this side and I have 180 on this side, which means overall I'm going to have more kilojoules over here. So I need to say, well, I have 180 and I have 112, so I need to cancel out this 112 by subtracting it from the 180. If I do 180 minus the 112, I end up with 68 kilojoules. So it takes 68 kilojoules. Ultimately, this is my answer. My problem is done. I know that this reaction is now endothermic, and my 68 kilojoules can stay there as a reactant. If I were to pull them out and rewrite that equation or answer this up here, because it's a reactant, I would put 68 kilojoules. Okay? Let's take a look at another example. We have to look at the example of graphite going to diamond. Okay, we're going to look for the delta H of this reaction. And I have two partial step reactions. So I have graphite plus O2 becomes CO2, and I have carbon diamond plus O2 goes to CO2. These are both exothermic processes, so I can go ahead and put 394, oops, that should be a 4, 394 kilojoules there, and 396 kilojoules there. So O2 isn't a part of this reaction, and CO2 isn't a part of this reaction, but graphite is, and diamond is. So I'm going to go ahead and rewrite these equations so that graphite and diamond are on the proper side. So let's start with graphite. That one's good. So C graphite plus O2 yields CO2 gas plus 394. Oh my goodness, I just can't write that 4, can I? 394 kilojoules. Now, diamond is diamond is a product, and so I'm going to reverse this reaction, making sure to line up Let's see, of course my pen doesn't want to write now because I wrote that 4 wrong. So for this one now, I'm going to go ahead and reverse this one. So I want my diamond to be a product, so I'm going to write, I like to keep the numbers to the outside, but it wouldn't matter if you did or not. But I like to keep this 396 kilojoules out here, plus CO2 gas. It wouldn't matter what order you wrote this in. I just think it's easier to always have the numbers on the outskirts. It goes to C diamond plus O2. Okay, there's my two equations. I'm going to go ahead and look and see what things I have on opposite sides of the arrow that I can cancel out, and that happens to be the CO2. Okay, it can also be the O2. So now I have this C graphite going to C diamond, and I have 394 kilojoules over here and 396 kilojoules over here. So I have more kilojoules over here. I have 2 more kilojoules over here. So I have 2 kilojoules. And that can be my final answer. Or, again, this is endothermic, so this reaction is plus 2 kilojoules if I wanted to put it back up there. Let's try one more example. So sulfur solid plus O2 yields SO2. My delta H is something that I'm looking for. And there I have my 2 equations. Okay, so again, this one is positive, so it's endothermic, so 790.4 kilojoules. This one is exothermic, so plus 198.2 kilojoules. I'm going to look for things that are unique in here and unique to up there. So I see sulfur and I see sulfur. So that's a good start that I see. See O2 several places. That's not going to help me much. Oh, but I see SO2 and I see SO2, and that is also unique. SO3 is an intermediate, so we're hoping it's going to get canceled out. So let's start with my sulfur, which is a reactant. You might notice that this is a single sulfur and this one is doubled. We'll worry about that at the end. I'm just concerned with getting the proper things on the proper sides. So I have 790.4 kilojoules plus 2S solid plus 3O2 gas yields 2SO3 gas. Okay. The other thing I'm concerned with is getting this SO2 on this side. So I'm going to reverse this whole equation. You notice I'm not paying too much attention to what the final ending situation is going to be. But I'm going to reverse this one and put this 198.2 kilojoules plus 2SO3 gas, which is going to yield 2SO2 gas plus O2 gas. Okay. Okay. So I'm looking and I'm sort of seeing that a lot of this is doubled from what I need. But it looks like things will cancel out, and that's good. So I'm going to go ahead and add this together and work with it this way, because it doesn't matter what order I solve this problem in. So if I look here and I have this intermediate, this 2SO3, so I can go ahead and cancel that out on both sides. I have 1 oxygen over here and I have 3 oxygens over here, so I'm going to cancel this one out and I'm going to bring this one down to 2. Essentially I'm subtracting 3 minus 1 and giving me 2. And now I'm going to go ahead and add this reaction up. So I'm going to have 2S solid plus 2O2 gas yields 2SO2 gas. And I notice that everything is doubled, but I'm going to go ahead and just add this up. So I'm going to add up my 790.4 plus my 198.2, and I'm going to end up with 988.6 kilojoules. I just need to go through and divide this by 2. So I went through and I divided it in half, and you can see I have 494.3 kilojoules because I divided